All right, we're going to continue with a few more Arabic Islamic mathematicians. This is Thabit ibn Qurra. He lived in 836 to about 901 AD. He was from northern Mesopotamia. That still exists, though it's not the power it was then. He moved to Baghdad as an adult, and he joined with the translators working on mathematical texts in the House of Wisdom. So he did join the House of Wisdom. We're not quite sure exactly when, but we do know it was after he was an adult. He did additional work extending some of the number theory sections of elements. This would be the translated version of Euclid's Elements. Remember that when the Arabic and Islamic scholars were in Alexandria, they didn't just copy. They weren't just like monks in the Dark Ages in Europe who were just translating word for word. They knew something about mathematics, so they corrected, edited, added comments, and rewrote the elements into their language. So that happened, and then he added to that when he was in the House of Wisdom, basically extending it, not necessarily making it bigger, but making the chapters on number theory bigger. So again, these aren't really like books. They're more like scrolls at this point, though we are still calling them books. And some of you saw probably this picture specifically when you were looking for a proof to do. And this is a Chinese version of a Chinese Go board, though it's not quite a Go board, but come on. All right, maybe it's not very big, but you can see the triangle here, and then you can see the same triangle here, right, and so on down the line. And one of you, I don't remember which one, did a proof very similar to this, and so Thabit ibn Qurra had created a dissection proof of the Pythagorean theorem, which is considered equivalent to this Chinese Go-Gu construction of it. This is the one where the C side is out here, right? And maybe this one is A. Let's put it in here, A. And maybe this one is B. So on this side it's A, right? And on this side it's B. And the question becomes, well, how big is this box, right? That middle box, because that's not included, right? That's the piece that's not included in these other triangles, right? And these are all the same triangles, but you would have basically C squared, that's the outside, right? And then you would have, well, that should be equal to the sum of the four triangles and that little one, right? So it should be equal to, what would that be? 4 times 1/2 base times height, so AB, A times B, plus, how do we want to define that, right? So we'd have to figure out how we want to define that. Oops, not this. It would be equal to that plus this little shaded square. And we could use something like B minus A or something like that, right, to define that piece. Some form of, however in terms of A and B, we define that space. So we'd have whatever that is. Anyway, Thabit ibn Qurra, his obviously didn't use the Go-Gu construction, but it is equivalent to that. It is essentially the same thing. In that one, if I recall right, we specifically make it a B minus A, but in this one, you're using it a little different. But yeah, so that's Thabit ibn Qurra. He did a lot more than that. This is just a brief overview, right? And then we have Omar Khayyam. Omar Khayyam is older, or was around later. So 1040 to 1123, Common Era or AD. But he was from Persia, Iran, which would be considered Iran. He is not associated with the House of Wisdom in Baghdad, though some of his works ended up there, but he wasn't purposely trying to get the stuff there. He was known as both a poet and as a mathematician, an astronomer, and a philosopher. I don't have a lot about Indian mathematicians. I will mention that there are some Indian mathematicians that were very big on the poetry, and that is where the first experience with the sequence that will later be called Fibonacci sequence comes from. So poets use math as a regular basis, so do astronomers, philosophers, and mathematicians. His biggest mathematical contribution, and this feels being very light with that statement there, because we have a bunch of proofs for the Pythagorean theorem from him and other stuff, but his mathematical contributions were based on what was not yet called algebra, but it was ideas from Al's work, and he used that method and geometric methods to solve various sorts of cubic and higher degree equations. And by that I mean like 4th degree, 5th degree, etc. It's theorized that he had multiple steps, or there's multiple types of cubic equations. There's monic, there's depressed, there's all this other stuff. And that's true for all of them above quadratics, technically. Quadratics are above, though they don't all have as many. Quadratic obviously has less. There's only, the 2 degrees. But in each one, there's different forms that they may take. And he knew how to solve a few cubic equations, like created a cubic formula for this type and a quartic formula for this type. Not a general quartic or a general cubic, but a quartic, cubic, quintic, etc. for particular types or forms of problems. That's how we would call them now. We would separate them by, it has these pieces, it doesn't have this piece, so it's this type. He definitely went beyond the Greeks here, like way beyond the Greeks. In fact, it would take a while for this to get to medieval Europe, and we won't actually talk about other people who go that far really exclusively until the Renaissance. So it took Europe a while to catch up. How does this work? Let's talk about this. So this is Joseph's model for the history of math during the Dark Ages, which is what we're talking about. So the Hellenistic world, this is Greece, right? If you don't know, that's Hellenistic. The pre-Greek Hellenic period is before Greece as a country, right? But we're talking about, that includes Greece, okay? And then we have Sicily, that's Italy. We have Western Europe. Western Europe is things like Britain, Ireland, Scotland, all of those countries that are very west side. It doesn't include Spain. You'll notice that there is a couple places for Spain, Toledo and Cordoba. There does include Cairo down here, and it shows Egypt, or it shows Baghdad. Cairo, so again, Alexandria is gone. Cairo is the next central hub there. So it's kind of like prior to this period, we would have Alexandria here. And a lot of stuff from this, which is in Egypt, would go here, right? But it didn't go elsewhere. Some of it went to Greece. In the beginning, a lot of it went to Greece, but later on, just a little bit. So Alexandria would go to Baghdad. From here, this is where we start seeing stuff, okay? So Dark Ages happen. We kind of established that. And we're not talking about the Dark Ages in Europe yet, though this includes Europe. That's going to be next. But I want to touch base on this first. So a lot of the knowledge coming into Baghdad that didn't happen for Alexandria, right? So the knowledge from Alexandria, a lot of it came from Greece or Egypt, right? We don't have a lot from outside of there. That was the pre-Dark Age. When we get to the Dark Age, everything's coming into Baghdad. Everything. So Indian mathematics into Baghdad. Indian mathematics also went to China. Indian mathematics also went to Greece. Chinese mathematics went to Baghdad, went to India, went to Persia, which would be Iran, but Jandi Shapur in Persia. And I probably, again, no offense is meant by my pronunciation. Please never take it that way. I try to pronounce them as well as I can. And Indian mathematics did go to Greece, but it also went to Persia. And then the Persian mathematics also went to Baghdad. So we have Baghdad getting stuff from India, from China, from Persia, from Greece. We have stuff from Greece. We also have stuff from Greece going to India and to Persia. And then we have stuff from Greece going to Sicily. But from Baghdad, that's where it's all coming in, right? So this is, and as I mentioned, the Alexandria stuff, all that, it comes in here to Baghdad, and then Baghdad wants to share it, right? Because who doesn't want to share knowledge? Nobody wants to hoard knowledge, and we hope. And of course, most of you are going to be teachers, so you don't want to hoard knowledge. You want to share it with your students so they become better and can move on and can take those ideas and expound upon them and turn them into something amazing. So Baghdad was sending stuff to Sicily in Italy, which will make a difference to the Renaissance later. But they were also sending stuff to Cordoba, and from Cordoba it would go to Toledo. The reason why Spain was such a big hub is because Spain at this point was controlled by both Christianity in the Castile areas and by Muslims in the other parts. So it was and again, I'm saying Spain like Spain was a country, right? So it's really not yet. This is where we're going to see it form. But we have this place, this part of land that is in these different baronies or whatever as we want to call them. That was also happening in Europe. It was happening in Sicily. So the idea of calling like France a place right now is silly because it was the Gauls, however it's pronounced. The Germans, so that's technically an American word, or some other countries, it's not their word. They would call themselves Deutsch or Deutschlanders. So, like, a lot of these countries weren't countries yet. So we are talking about them kind of like they are. Persia is where modern day Iran is. A lot of Iranians can trace their lineage to Persian ancestors. So that's true of a lot of these. This is not Iraq, it's Baghdad at this point. And they sent stuff to Sicily and Spain. Spain became a big hub for translations. A lot of the people in Spain knew and could speak both Latin, which was a predominant language at the time for Europe, for a lot of Europe, but they could speak Arabic and could read Sanskrit and stuff like that. So they were translators. These two places, Cordoba and Toledo, become hugely essential to the translation and the spread of knowledge into Western Europe from Baghdad. As a weird side note, maybe, there is a Muslim named city here in America. And it is an old city. It has been around for a very long time. And the reason that it's a Muslim named city is because it was a name of a place in Spain, and it was named by the Muslim people. And when the Spaniards came to America, or the Americas, the whole thing, and they settled up here in what we would call the United States, they named a bunch of cities off of places back home. And in fact, the oldest city in this state, in this country, the oldest still active city is a city in Florida that I don't remember the name of it, but it was from the Spanish before the English and the rest of the Europeans, the Western Europeans got here. It was named, and it was in Florida. And it's just named after a Spanish place. Anyway, the only American city that's named after a Muslim, has a Muslim name, is Albuquerque. Albuquerque is a Muslim word for a place in Spain, but at the time that it was done, it was in Muslim-controlled Spain. So it wasn't even Spain then. But yeah, so that's an interesting thing. Their information from Baghdad and from the House of Wisdom did go to Cairo, and from Cairo it went into Spain. Spain, in the different places, the two big cities, so Cordoba sent stuff to Western Europe and to Sicily, and then Toledo did exactly the same thing. Sicily did distribute some to Western Europe. So we have this huge spread of knowledge happening. Okay. I do want to say that I've mentioned this before. Biases are everywhere. So there are biases. Some biases are unintentional. We don't know enough about the past, or we think we know, but we really don't because there isn't enough detail. So that happens. So here's was Islamic role just transmission? This is a common thing that has been taught in schools on a regular basis, that the Islamic people, all they did was transfer everything from the House of Alexandria. And quotes from this idea by Morris Klein, one of the authors of some of the books that are very useful. A significant contribution to mathematics that we owe to the Arabs was to absorb Greek and Hindu mathematics, preserve it, and ultimately transmit it to Europe. He also said the Arabs did make critical commentaries of Euclid's elements, which is surprising because they show appreciation of rigor despite their usual indifference to it in algebra. These are all from him. There's a widely held view that after a brilliant period of mathematics, when the Greeks laid the foundation for modern mathematics, there was a period of stagnation before the Europeans took over where the Greeks left off at the beginning of the 16th century. That would diminish the work that the Europeans did prior to the 16th century, and I think that's not cool either. The common perception of the period of 1,000 years or so between the ancient Greeks and the European Renaissance is that little happened in the world of mathematics, except that some Arabic translations of Greek texts were made which preserved the Greek learning so that it was available to the Europeans at the beginning of the 16th century. That would diminish Omar and Al and Thabit and all the rest of them. That such views should be generally held is of no surprise. Many leading historians of mathematics have contributed to the perception by either omitting any mention of Arabic Islamic mathematics in the historical development of the subject, or with statements such as that made by Duhem, a historian. Arabic science only reproduced the teachings received from Greek science. Recent research points a new picture of the debt that we owe to Arab Islamic mathematicians. And by recent, I mean in the last 50 years, okay? Because history's funny. We will discover stuff, and it'll take a long time for that stuff to be written into papers and published. So, Certainly, many of the ideas which were previously thought to have been brilliant new conceptions due to the European mathematicians of the 16th, 17th, and 18th century are now known to have been developed by Arab or Islamic mathematicians around 4 centuries earlier. In many respects, the mathematics studied today is far closer to that of the Arab Islamic contribution than to that of the Greeks. This is very true. In fact, you guys spend more time studying Arab mathematics than you do studying Greek mathematics. Think about how much time you spend in algebra classes. Before proceeding, it's worth trying to define the period that we are covering and give an overall description to cover the mathematicians who contributed. The period covered is easy to describe. It stretches from the end of the 8th century to about the middle of the 15th century. Giving a description to cover the mathematicians who contributed, however, is much harder. There are works on Islamic mathematics detailing Muslim contributions to mathematics. Other authors tried the description Arabic mathematics, even though all of these mathematicians were not Arab. I mentioned Omar was Persian, right? However, certainly not all the mathematicians we included were Muslims. Some were Jews, some Christians, some of other faiths. The regions from which the Arab mathematicians came was centered on Iran, Iraq, but varied with military conquest during the period, which was very true of the Mesopotamia time frame. As its greatest extent, it stretched to the west through Turkey and North Africa, to include most of Spain, and to the east as far as the border of China. The background to the mathematical developments which began in Baghdad around 800 AD is not well understood. Certainly there was an important influence which came from the Hindu mathematicians, whose earlier developments of the decimal system, yep, we had it before the 800 AD, was important. There began a remarkable period of mathematical progress with Al's work and the translations of Greek texts. This period begins under Caliph Harun al-Rashid, the 5th Caliph of the Abbasid dynasty, whose reign began in 786. He encouraged scholarship and the first translations of Greek texts into Arabic, such as Euclid's Elements by al-Hajjaj. Again, no disrespect is ever meant by my inability to pronounce these correctly, which were made during al-Rashid's reign. The next caliph, Mamun, encouraged learning even more strongly than his father, al-Rashid, and he set up the House of Wisdom in Baghdad, which became the center for both the work of translating and for research. Al-Kindi, born in 801, and the 3 Ban Musa brothers all worked there. It's very much believed that the Ban Musas, and I don't talk a lot about them, but they were amazing, both showmen and science and mathematics. And they had their specialties, of course, but they all lived and resided in there. They were actually, some say they were orphans of the state, of the land, and they were brought in. They were brothers that stayed together, and they did tend to look alike. In all the pictures that we have, which are not real pictures, they're all sketches and artist renditions, but they resided in the library, just like Hypatia in the Library of Alexandria and some of the others. They may not have been born there, but they resided there from a young age and spent their time in the library. One should emphasize that the translations into Arabic at this time was made by scientists and mathematicians, such as those previously named above, not by language experts ignorant of mathematics, and the need for the translation was stimulated by the most advanced research of the time. This is that big difference. These people are not just writing word for word what was said, because languages don't work that way. If you translate Spanish word for word in the order it is said, it will not make sense in English. Vice versa is true. If you translate English word for word into Spanish words, it will not make sense. Anyone who speaks more than one language knows that that is the case for most languages. So it's more than just being able to translate it. It's being able to understand mathematics and translate it and correct it if need be, but also to add commentary and to expound upon it. It is important to realize that the translation was not done for its own sake, but was done part of current research. Al's work with elements was not because he wanted to translate elements. It was because he was going through elements, making commentary, adding to. Same thing with Thabit and Omar and all of the rest. Most of the important Greek mathematical texts were translated, and lists of these exist. Algebra was a unifying theory which allowed rational numbers, irrational numbers, geometric magnitudes, etc. to all be treated as algebraic objects. Now, we won't have that word yet because the word algebra does not mean how we take it to mean at this point, but this is all being set up now, or in this time. It gave mathematics a whole new development, path so much broader in concept to that which had existed before, and provided a vehicle for future developments of the subject. This is where we can really separate what is arithmetic, what is number theory, what is geometry, and even trigonometry, which is a separation from geometry to trig. But we can start seeing the separations. No, we haven't seen calculus. Yes, we've seen some discrete, but we haven't really connected those dots yet. But we have the beginnings. Another important aspect of the introduction of the algebraic idea was that it allowed mathematics to be applied to itself, not to outside things, but to itself in a way which had not happened before. One commentary states Al's successors undertook a systematic application of arithmetic to algebra, and algebra to arithmetic, both to trigonometry, algebra to Euclidean theory of numbers, algebra to geometry, geometry to algebra. This was how the creation of polynomial algebra, combinatorial analysis, numerical analysis, the numerical solutions of equations, and new elementary theory of numbers, and the geometric construction of equations arose. We really start to see how broad math is from a basic understanding of counting, which is where we started. So this is pretty huge. And we're excuse me. We follow the development of algebra for a moment and look at Al's successors. About 40 years after Al's is the work of Al-Mahini, born in 820, who conceived the idea of reducing geometrical problems such as duplicating the cube to problems in algebra. Abu Kamil, born in 850, forms an important link in the development of algebra between Al's and Al-Kharajis. Despite not using symbols, but writing powers of X in words, he had begun to understand what we would write in symbols as, that didn't show up real well on the PowerPoint, x to the power of n times x to the power of m is equal to x to the power of n plus m. And I'll put parentheses just to be clear. So despite not using symbols, but writing powers of x or powers of a variable in words, again, they wouldn't have used x, he had begun to understand what we would write using that symbolic notation. I want to remark that symbols did not appear in the Arabic mathematics. They didn't appear until much later. It became a lot to write. So we'll see a few at the end of the Dark Ages for medieval and for Europe. And then in the Renaissance, we start to see the development. Ibn Albania and Al-Khalasadi used symbols in 15th century, and although we do not know exactly when their use began, we know that symbols were used at least a century before this. Technically, Al-Khwarizmi was familiar with what I would call Idra Hindu numbers, or the Garda Hindu, whichever you decide it starts in. or you do the research and find out exactly where it starts. There's a nice research paper. Anyway, those symbolic symbols like 1, 2, 3, right? All of these. That's symbolic symbols. So symbols were used way earlier. That's what these are. These are symbols. 4 represents 4 of something. 7 represents 7 of something, right? So we do know that the symbols were kind of being used, though a lot of the Arabs didn't use them to be clear, so they wanted to be very specific, but they will start using them in their own math. Omar gave a complete classification of cubic equations and geometric solutions. He also wrote that he hoped to give a full description of the algebraic solution of cubic equations in a later work. If the opportunity, and he said, if the opportunity arises and I can succeed, I shall give all these 14 forms with all their branches and cases and how to distinguish whatever is possible or impossible, so that a paper containing elements which are greatly useful in this art will be prepared. That was technically what he's, translated, but what he said. So he was already planning that. I don't think I know that this was ever published or put into a paper, or it could have been put in a paper and we just haven't found it, right? We're not that interested, which is sad. Indian mathematics is without a doubt that mathematics today owes them a huge debt. And there's been a ton made by Indian mathematicians, though in the West, we tend not to know a lot of them. Same thing with the Chinese mathematicians. What is surprising is that there has been a reluctance to recognize this, and one has to conclude that many historians of mathematics found what they expected to find, and perhaps even what they hoped to find, rather than to realize what was so clear in front of them. We shall examine the contributions of Indian mathematics now, but before looking at this contribution in more detail, we should say clearly that the huge debt is the beautiful number system invented by Indians on which much of mathematical development has rested. Laplace put this with great clarity. The ingenious method of expressing every possible number using a set of 10 symbols, each symbol having a place value and an absolute value, emerged in India. The idea seems so simple nowadays that its significance and profound importance is no longer appreciated. Its simplicity lies in the way it facilitated calculation and placed arithmetic foremost among useful inventions. The importance of this invention is more readily appreciated when one considers that it was beyond the two greatest men of antiquity, Archimedes and Apollonius, to come up with. That's pretty huge. All right, I'm going to go into Indian mathematics off of this.